So today we will see the truncation error for Crank-Nicolson method. So the truncation error for Crank-Nicolson method. So this is an implicit method for solving heat equation. So let's see. So we will solve this ut equals to c square uxx. Means basically this is the heat equation, and we will see that after the finite difference approximation, what is the truncation error. So what we will do, we will approximate this heat equation at the point xi and Tn plus half. So what does mean? So suppose that this is my xith level and this is my, this point is at Tn level, this is Tn plus half and this is Tn plus 1. So of course this distance is k by 2 and this distance is k by 2. Okay, so it means that we have the spacing between any two time level is k. So what, so we have to find, we will approximate ut at xi and Tn plus half. We have to find out this for the Crank-Nicolson method. So for this, what we will do, we will write the Taylor's expansion of u around the point Tn plus half. So we'll first move to this point Tn plus 1 and then we'll move to this point, and using these two we'll find this ut xi and Tn plus half. So uxi Tn plus half plus k by 2 is this nothing but u at xi comma Tn plus half plus k by 2 u at u derivative t derivative at xi and Tn plus half plus this k by 2 whole square ut by 2 at xi and Tn plus half plus k by 2 whole cube u t by 3 factorial at xi and some xi. So this xi1 lies between your Tn plus half and Tn plus 1. Yes. So u at xi Tn plus half is equals to uxi Tn plus half plus k by 2 ut xi Tn plus half plus k by 2, means it's a usual Taylor's expansion. Now we will do the same for the uxi Tn plus half minus k by 2. So let's do the uxi Tn plus half minus k by 2. So you evaluate uxi Tn plus half minus k by 2. So this will be the same. I will apply uxi and Tn plus half minus k by 2 uxi comma Tn plus half plus minus k by 2 square utt xi and Tn plus half divided by 2 factorial plus minus k by 2 cube uttt xi and some zeta 2 where divided by 3 factorial, where this zeta 2 will lies between Tn and Tn plus half. Okay, so now we have two equations. The first equation, and what we are supposed to find out ut at xi and Tn plus half. So we have to find out this value. So we have to find out this value, this value, this value. So what we will do, we will just subtract this equation to the new equation, this. So after subtracting, let's subtract this with that, what we will get. So subtracting both will give me this. See, now see that this is nothing but Tn, and this is nothing but your, this is nothing but your Tn plus 1. Okay, so this is nothing but Tn plus 1, and that was Tn. So now let's subtract these two. So what we will get after subtracting? So after subtracting, we'll get this. This will be u at. So I should write u at xi and Tn plus half plus 1 minus u at xi Tn is equals to this term will be cancelled and this term will be cancelled. So these two terms will cancelled out. The remaining will be this, and this will be plus k, and u at xi Tn half plus k cube by 24 utt at xi and some zeta, where this zeta lies between Tn and Tn plus 1. Yes. Now we'll see. So now we can find out your ut at xi and Tn plus half. So this will be u at I n plus 1 minus ui n divided by k plus k square by 24 utt t xi zeta 1. So this is what we see. So for the ut, we are getting the truncation error at this. So this is the truncation error only for ut. This is the only for ut. Now we have to find the approximation for ux also, uxx also, and after getting the truncation error for uxx also, we will just substitute this all utt and uxx in our heat equation, and finally we will get the final truncation error. So let us now approximate the uxx. So uxx is approximated by, so this uxx is approximated by the average of FDM at Tn level and Tn plus 1th level. So this is approximated by the average of FDM at the time level Tn and Tn plus 1. So let us see that how we'll write. So again we'll write that xi. So now we'll move to the xi to the edge. So this is your thing. So this is your xi. So we'll move to xi plus h, and we'll move to xi minus h. So u at xi plus h and Tn. So if you calculate it, so we'll get u at xi Tn plus h u at so h u at xi, so u x at xi comma Tn plus h square by 2 factorial u xx at xi comma Tn plus h cube by 3 factorial u xxx at xi comma tn plus h4 by 4 factorial u x some eta 1 and tn. So where this eta 1 lies between your xi and xi plus h. So xi and that is your xi plus 1. Okay. Yes. Yeah. Okay. So this is the thing. So h cube by 3 factorial u x x by tn. Okay. So why we have gone for the fourth derivative? Because see, this time we have to approximate. This time we have to find out the value of this u double x, double derivative. So if we so this time we are not going to subtract. This time we have to add, because see, in the last expression what we have observed that what we have observed for the last, see that the even term gets cancelled out. So here we see that the even term gets cancelled out. So since even term is getting cancelled, so for getting UTT, see, for getting UTT we'll go to the fourth derivative, and since we are doing the double derivative, that's why we went for the fourth derivative. So now we have done this. Now what we'll do, we'll again do the minus h and tn. So the same will come. So this will be u at xi comma tn and minus h u x xi tn, so plus h square by 2 plus h square by 2 u xx xi and tn plus h cube by 3, so it will be minus, so it will be minus h cube by 3 u xxx tn plus h4 by 4 factorial some eta 2 comma tn, where this eta 2 lies between xi minus 1 and xi. So now see, we have two equations. Now if we'll add these two, so if we'll add these two, we will get our u xi plus 1. So adding these two, so adding this 2 will give me, so u at xi plus h will give me u I plus 1 at n minus plus u I minus 1 at n is equals to 2 times u I n plus h square or h square u h square u xx at xi and tn plus, let's see, yes, so if we'll add this, so this is 24 and this is 24, so we'll get 12. Okay. So we'll get h4 by 12. So h4 by 12 u fourth derivative at some eta, where this eta lies between xi minus 1 and xi plus 1. So you see we get at the value of this. So if we calculate uxx xi and tn, so this will give me ui plus 1n minus 2 uin plus ui minus 1n divided by h square plus this term h4 by 12 uxxxx at eta and tn. So this is the, now see at the beginning we told that we will take the average of uxx at tn and tn plus 1. So in the same way we can get uxx at xi and tn plus 1, that is equal to ui plus 1 n plus 1 minus 2 ui and n plus 1 plus ui minus 1 n plus 1 divided by h square plus some error h4 by 12 uxxxx some eta tilde tn. Now if we'll add and divided by 2, so we'll get uxx at xi and tn plus 1. So we'll get at the, since we are taking the average of these two, so let's suppose that this, so this will be, we are taking the just the what you call the average of this. So uxx, so let me write on the uxx. So now my uxx at ith level will be, if we'll add these two, so 1 by 2 of these two, so 1 by 2 of this ui plus 1n plus 1 minus 2 ui at n plus 1 plus ui minus 1 n plus 1 divided by h square plus ui plus 1n minus 2 uin plus uin divided by h square, and plus the error term will be this. So plus, so you see the h square is there, so this won't be, so this will be, so it will be h square, and it will be h square because this h square will cancel, no? So here h square is there, yeah. So plus, so h square plus h square by 12, so h square by 12, and so some uxx at some eta, let's write eta 1 or eta 2, that you can write anything, or eta 1 or eta star, let's write eta star. So this is the truncation error for UTT. So now we can try, you can find out the net truncation error, that will be your, so ut equals to c square uxx is there. So from here, so ut, we know that what is that, so this will be nothing but ui at n plus 1 minus ui at n divided by k plus some k square by 24 utt at some zeta n, some xi and zeta, and this equals to or some expression, something, the big expression, plus your error, that will be, that was your h square by 12 u xxxx zeta tn. So let's write this plus u x, so h square by 12 at some zeta and eta tn. This zeta lies between xi minus 1 and xi plus 1. So the truncation error will be, if I let's say the c square will be there, c square will be there, c square is also there. So c square is also there multiplied with, let me write c square, yeah. So this, so if I'll take this to the right hand side, so it will come this with negative sign. So this whole will be the error. This whole will be the truncation error. So this is the truncation error for the tail. Crank-Nicolson scheme. So this c square h square u x by 12 at some eta tn minus this k square by 24 u t t t. So this is the error term. So this is the truncation error. So we have determined the truncation error in the above in this approximation. So, okay, thank you.